Okay, I'm going to just talk about this. This is labeled 4.7 because we really need to talk about this later. But so I'm going to revisit this once or twice throughout the course. But for this section, for chapter 3, we can introduce this topic. The topic Lhopitals rule can be introduced. Now, I can't introduce Euler's method yet, but I'll do that at the end of chapter 4. So basically, let's just talk about Lhopitals rule. If you have a limit of the form f of x over g of x as x approaches a, and the limit of the numerator is 0 and the limit of the denominator is 0, then you actually get the indeterminate form 0 over 0. Now, one such limit is sine x over x, and we learned from the squeeze theorem earlier that the limit of sine x over x is 1. Here's another limit, tangent x over x squared, that if you plug 0 in, you're going to get 0 over 0. But what happens here, if you try to evaluate this limit, you can actually break sine x, tangent x up as sine x over cosine x, and you can put the sine x with one of the x's in the denominator, and then the cosine x that's in the denominator from tangent x, you can put it with the other x. And we know this limit is 1, but of course we know this limit would have to be 1 over 0. So 1 times 1 over 0 would be undefined. So the point is that these limits that have this form 0 over 0 might actually exist and equal some number 1, or they might be undefined. There's another example here that I used, the limit of x over sine of x cubed, and what I did is I had the limit, I wrote that, I multiplied the top and bottom by x squared over x squared, and that gave me the limit of x cubed over x squared sine of x cubed. Well, I can break this up using properties of limits as limit of x cubed over sine x cubed times the limit of 1 over x squared. Well, you might remember that anytime we have the limit of sine of theta over theta as theta goes to 0, that's 1. Well, we can treat this the same thing. X cubed can be our theta. So, except one thing you could say, you could also write this limit another way. So you could also say the limit of theta, and I'm saying theta just not to get it confused with the x down here. The limit of theta over sine theta as theta goes to 0 is 1, because basically you're just getting the reciprocal of this. So the limit of the reciprocal of this is just going to be the reciprocal of 1, which is also 1. So the limit of x cubed over sine of x cubed is actually 1. So there you're going to get 1 times 1 over 0, which is also undefined. And there are some other indeterminate forms that you can run into later. But now we're just going to focus on the form 0 over 0. Basically what Lhopitals rule says, it says that, if f and g are differentiable on an open interval such that the derivative of g is not 0, then basically f of x over g of x will have the form of 0 over 0 as x approaches a from the right. And so the limit as x approaches a from the right of f prime of x over g prime of x is actually going to equal the same as the limit of f of x over g of x as x approaches a from the right. And so in most cases, you don't have to approach a from the right. You can just approach a in general. But let's go ahead and take a look at how this would apply. If we wanted the limit of sine x over x, first thing we'd have to do is make sure that when we try to evaluate this, we get the form 0 over 0. Well, obviously sine of 0 is 0, and as x goes to 0, x is 0, so we get 0 over 0. So Lhopitals rule will apply. So all I do, now you don't take the derivative of the entire function, you only take the derivative of the numerator and then you take the derivative of the denominator, and you do these two as two separate functions. Now the derivative of the numerator is cosine x, the derivative of the denominator would be 1, and there should be an equal in there, but now that's going to give me limit of cosine x over 1, and cosine of 0 is 1, so that's just 1 over 1, which is 1. So that was much easier than that squeeze theorem that we used earlier. Here's another example, the limit of natural log of x over x minus 1. Well, the natural log as x approaches 1. The natural log of 1 is 0, and 1 minus 1 is 0. So this has the appropriate form. So then I take the derivative of the top. The derivative of natural log of x is just 1 over x. And then the derivative of the bottom is just 1. And since 1 over x over 1 is just 1 over x, then the limit would be the limit of 1 over x as x approaches 1. So, and that's just going to be 1. 1 over 1 is 1. Now, I've got some other functions here, but I actually am giving you these functions a little bit before their time. But you can return to this video after we do the chapter on logs and exponential functions, because right now you don't have the tools to find the derivatives. But so just what I'm going to ask you to do here is just trust me that when I give you the derivative of a function involving an exponential or a log function, that it's correct. Okay, but you can evaluate these functions. So if we let x go to 0 here, the top's going to be 0 times sine of 0, which is 0, and the bottom's going to be 1 minus e to the 0, which is 1 minus 1, which is 0. So the rule would apply. So you can use the product rule here, and I'll leave you to do that on scratch paper, but I got sine x plus x cosine x, and then again, just trust me that the derivative of this function is 2x e to the negative x squared. Now, if you take the limit of this function as x approaches 0, you get 0 on top and 0 on bottom. So this still has the form 0 over 0, so we can apply the rule again. Now you're going to take the derivative of sine x plus x cosine x, and so you're going to take the derivative of sine x and get cosine x, and then you're going to have to use the product rule on this portion, and then you just combine your like terms, and you should get 2 cosine x minus x sine x. And again, just trust me that the derivative of 2x e to the negative x squared is 2e to the negative x squared minus 4x squared e to the negative x squared. Now, as x approaches 0, the top's going to give you 2 times cosine of 0, which is 2, and the other term's just going to go to 0, so the top's 2 minus 0. And on the bottom, as x goes to 0, I get 2 times e to the 0, which is 2, and then minus this is going to be 0 when x goes to 0, so the bottom's going to be 2 minus 0. So I get 2 over 2, which is 1. Now, you can also use Lhopitals' rule in some cases where you have infinity minus infinity. Here, if you let x approach 0 from the right, then 1 over x squared is going to go to infinity, and 1 over sine x is going to go to infinity. So this limit would be of the indeterminate form infinity minus infinity as x approaches 0 from the right. So what you can do here is you can get a common denominator of x squared sine x and just add these two fractions together, and you'll get sine x minus x squared over x squared sine x. Well, now if you evaluate this at x equals 0, it has the form 0 over 0, so we can apply the rule. So you can take the derivative of this. The top part's pretty easy. The derivative of the top is just cosine x minus 2x. Now on the bottom, you're going to have to apply the product rule. Okay, so I got x squared cosine x plus 2x sine x. Now let's try evaluating it as x approaches 0. The top, we're going to get cosine of 0, which is 1, minus 0, so the top's going to be 1. But the bottom, since I have factors of x in both, is going to continue to be 0. So 1 over 0 is what I get. Well, 1 over 0 generally is going to approach infinity or negative infinity. But since I'm approaching 0 from the right, you can plug in small values of x in here, like 0.01 or 0.001, and you'll actually see that this number is actually getting larger in the positive sense, so it must be approaching positive infinity rather than negative infinity. Well, since this limit is approaching positive infinity, then the original limit must be approaching positive infinity. Now, still the limit does not exist because that's not a real number. Now, this one, again, we also haven't talked about arctan. So when I talk about inverse trig functions, you can return and look at this example if you like. But actually, if you evaluate x times arctan of 1 over x as x goes to infinity, well, obviously x is going to go to infinity, but 1 over x is going to go to 0. Well, arctan of 0 is simply 0. So this is going to be the indeterminate form infinity times 0 as x approaches infinity. So what we can do to make infinity times 0 be of the form 0 over 0, all I have to do is, instead of writing it as x times arctan, how about writing it as arctan divided by 1 over x? Now that's the same thing as x times arctan, but by writing it this way, as x goes to infinity, I can see that 1 over x will go to 0. So the denominator is 0, and we already know that arctan of 1 over x is 0 as x approaches infinity. So that's 0 over 0, so the rule applies. Now just trust me that arctan of 1 over x is actually this function, and you know that when you differentiate 1 over x, you get minus 1 over x squared. Now, if I flip this over and multiply by minus x squared, I'm actually going to get a positive 1 on top, and the bottom is going to be 1 over 1 plus x squared. And then if you let x go to infinity, this term is going to go to 0, and you're going to get 1 over 1 plus 0, which is 1. So that means that our original limit up here must equal 1 as well. Okay, now you can actually use Lhopitals' rule for infinity over infinity too. So like here I have the natural log of x over x, and as x goes to infinity, the natural log goes to infinity, and obviously x would go to infinity, so this would be infinity over infinity. So what I can do here is I can apply Lhopitals' rule to this one. The derivative of natural log of x is 1 over x, and the derivative of x is 1. And so if you take the derivative, if you take the limit of 1 over x as x goes to infinity, obviously you will get 0. So this limit up here must equal 0 as well. Okay, now I've got a couple of other problems here. This one is 0 times infinity. And remember a while ago I did something like that where I wrote that as natural log of 1 over x so that it actually becomes the form infinity over infinity. Now if you take the derivative of the top, you get 1 over x, and if you take the derivative of the bottom, you get minus 1 over x squared. And if you use a little bit of algebra, you'll find that's just the limit of negative x as x approaches 0 from the right, and of course that has to equal 0. And I'll leave you with a couple of other tricks that you can do. Here's one where you deal with the limit of x to the x as x approaches 0, and that gives you the form 0 to the 0. And you actually have to use some tricks here to get this, but I'll just let you read this and see what I did and how I was able to evaluate this limit. And then on the last one, I'll just go ahead and scroll it on up so that you can see the whole thing, and then you can freeze the video if you want to see how I showed you that the limit of 1 plus 1 over x to the x as x approaches infinity is e, and that has the indeterminate form 1 to infinity. Now you may remember that in algebra or early in calculus you were told that this number e actually came from this limit, And so what's interesting is now I can show you using these steps that that limit actually does equal the number e. And again, you can return to these once you've covered the section on exponential and log functions.